Any questions before we begin? So I'll probably tell you a little bit about the midterm in a couple of minutes. I'm just going to wait to see if some other people show up to class. So before talking about the midterm, let me just give you like a quick summary of what happened last time. So last time we did the following. So we had systems of linear equations, right? That's what we're studying now. The idea is that you can always write the systems as AX equals B. So A here is a matrix of X is like the vector of variables or unknowns. So it's like XY or XYZ, etc., whatever you need. And B is like a known vector in a sense. And here B okay. So one way to think about the system of equations was like, if you think of the matrix A as a process, you have the matrix here. And you know the output is a vector B. So here is the output. So when you're trying to solve a system of equations, which is what we're going to do today, essentially what you're trying to find is like, can you find a vector X that you can feed into the machine, right, that will spit out B as the output, right? So you have to imagine that now you know the end result of your process, and you're just trying to know what you should give to the process itself to get that. Okay, so it's like some sort of like reverse engineering where you already know the answer and you're trying to find like the conditions that you have to put in place to get that answer. That making sense? So that's one way to think about solving a system of equations. Another interpretation was that here's a second interpretation, or that solving a system of equations that's trying to find whether some lines or planes or whatever are intersect or not. Solving AX equals B is like, it's the same as finding whether some lines or planes, plane, hyperplanes, like, etc., intersect or not. Okay. So that's a little bit more geometric. And from there, you kind of get something that's very important, which was the number of solutions, right? To the number of solutions. And you'll see this today to AX equals B. There are only three things that can happen. One, a possibility is like there are no solutions. Actually, there's no input you can find to produce that outcome or that output. So there are no solutions. So here is like 0 solutions. Like again, if you want to think about it geometrically, it could be like that I gave you two lines that were parallel, right? And so they can never intersect, so there's no solutions. Or there were two planes that were parallel. For example, if you also have taken like multivariable calculus, you have seen more about planes. But so like imagine like the something of that sort where like there's just like no point of intersection, no common point. There's another one which is like a unique solution. So here's like the number of solutions is one. And again, that corresponds to, like say 2 lines. If you intersect 2 lines, that will meet at a unique point if the lines are different and non-parallel, right? Also, like, you can work with planes, you can work it out. Like you can choose 3 planes in such a way, like if you start tweaking them a little bit so that they will meet the 3 of them at a single point, that also can be done. But yeah, so if you are clever enough, you can arrange things so that they will meet one time. And so here you have 0, 1, and the cool thing is that it kind of jumps to infinity, right? There's nothing in between. So after 0 solutions, 1 solution, it's infinite solution. So this is kind of like one of the most important things in this course. The solutions of systems of equations are either 0, 1, or infinite. Like you will never find 10 solutions, you'll never find 20. If you didn't find 0 or 1, it had to be infinite. It's kind of like they're like all exclusive, right? If you know that it cannot be infinite or 0, that also tells you that it had to be a unique solution, etc. So it's only 3 alternatives, and there's nothing else. Okay. And is that okay? So far, so good. Yes.
You have like 2 parallel planes and the plane that intersects both of them. Is that 0 solution?
Great question. So let's try to make a picture. Let's try to think about it. Oh, in fact, I can make a picture here. So I have a plane, right? Let's put another plane, right? And I put now one that's parallel. One that would intersect that, right? Like. Right, so now I have 3 pieces of paper, 2 are parallel, and then there's another one kind of cutting both of them, right? So right, this plane does cut this other one like in a line that looks like this, right? And the other one cuts, the same plane cuts this other one like in another line that maybe looks like this, right? So what would you say in this situation happens? Like, would there be 0 or infinite solutions? And at least it's clear that it should be 1 solution, right? Like that kind of seems like maybe more convenient, more persuadable. Would you go with 0 or infinite?
0.
Yeah, because the idea is that it is kind of like the common intersection. So it's not, they do meet at lines, 2 at a time, 2 of the 3, right? But you need the 3 to meet at the same place. So here, this is an example where there are no solutions, right? Because the common intersection of the 3 planes is trivial, is 0, right? Because the common intersection of all the planes of every plane of all the 3 planes is 0. It's empty, right? There's nothing in common between the 3s. It doesn't matter that 2 at a time do meet. You need them all to meet at the same place. Does that make sense? So yeah, there's a good example of where you need to be careful. Pictorially of how it would look like. Yeah.
So there was just 2 planes.
Right, like if I had, say if I had kept these 2, remove the one on the top, then there are infinite many solutions, which would be this blue line, right? Or if I had removed this one and just keep these 2, then there are infinite many solutions, which would be this green line. But we would have needed the green and the blue to intersect. And like in that case, the intersection would have been a point, because 2 lines, if they meet, would meet at a point. So it would have been like a unique solution. But like if the lines meet, like from the picture, it was kind of clear that they wouldn't meet because like these other 2 places were parallel. But yeah, does that make sense? Yeah, that's kind of, it's useful to think about that pictorially of how this looks like. And the last thing I was going to say about the mini summary of last time is that another interpretation, which for now, you don't have to worry too much about it because we'll use it a lot on the second midterm. So it's just like a heads up if you want. So here's another interpretation. that this system can be solved if you can write the vector B as a combination of the columns of the matrix A. If you remember, that's the last thing that I wrote last time. If you can express B as a linear combination of the columns of A. So like here, like you think of B as a vector, the columns of the matrix are vectors, and it's kind of like, can you add those columns in such a clever way that when you add those vectors together, you reproduce the vector B. And again, that's a useful interpretation, but we'll talk about that one like in the second half, like towards the second part of the second midterm or something. So we'll spend more time on this one. For now, you shouldn't worry too much about it. Okay, so today what I have to tell you is how do you actually solve systems. You'll find that solving systems is not that difficult. It kind of, you always do the same thing every single time. You just have to be careful because there are many operations involved in the sense that there's a lot of arithmetic that you have to do, a lot of multiplications, subtractions, additions, things like that. But it is very mechanical. So once you do a couple of examples that you understand really well, it's not that you have to do like 50 linear systems of equations. Like you after like 3 or 4, you kind of start getting like the picture of how everything is supposed to look like. Okay. Okay, before starting with the news material for today, let me just tell you about the midterm. Let's see. Okay, so you can go, I mean, I posted the same announcement in this other class, so it's like essentially the same that I'm about to show you. So if you, right, like in your campus site, there's also like an announcement that says something like information for the first exam. That's in 2 weeks from today, it will happen during class. So this PDF is more or less like a summary of like the basic material that you need to know for the exam. There's not that much like, you know, in terms of like formulas or like methods that you have to memorize. So it's more or less like what you see in those 2 pages. Like what I was going to say is that like for something like you know, like I mentioned it on the PDF, something like the rotation matrix, I would give you the formula for like the rotation matrix, and the point for you to memorize it. The other things like, you know, like say property, like let's say I think I wrote them here. Like properties of the transpose and the inverse that I had written last time, those you should know. I mean, more or less you should know like all the stuff that's on these 2 pages. Because the thing is like in this class, if I give you some sort of like formula sheet or something like that, with this, you kind of like ruin all the problems. Like because once you decide what you need to do, like really literally you just have to do arithmetic. So I cannot like, you know, value too much. I mean, hopefully everyone remembers how to multiply and add numbers, but that cannot be like, you know, the heart of the problem. The heart of the problem is like you realize, oh, I have to set it up this way, and this is how I start solving it. So like kind of like just setting it up correctly and things like that is kind of more valuable here, because like the solution itself is really not complicated in the same way in which it's complicated when you do like an integral or a derivative. Like it just has like a different like flavor, like the difficulty of the problems are not in that. So that's why we won't have like formula sheet, but if there's like something that would have been like very require like a memorization, like a rotation matrix or something like that, I would give that to you. But in general, like okay, just make sure that you do know everything that's written down on these 2 pages. And then just to again, it is the same on your Canvas side. So if you go to modules, you click on the matrices and vectors PDF. That's kind of the basic material that you need to understand for the first midterm. We're almost done with this. Like I'll definitely will be done by next Monday. Like all the material that you need to know for the midterm. This is more or less what I write in class. Like I do add a little bit more details to the class stuff, based also on your questions, like some examples that show up. But like it does have like all the important material. And then in terms of problems, well, you should check the examples we have done in class. You should also check the mini quizzes on Canvas and the assignments on the mirror side. But at least like in particular, these assignments on the mirror side are based on this PDF on the that I referred to. So if you like the problems that you need to study from this PDF are the ones that are under the the title or the topic matrices and vectors. So they're really 44 problems. There are a couple that you can ignore that I mentioned on this midterm guide. So you can check. I mean, they're like 4 or 5 that you don't have to worry about of these queries 44. Then so look at those, and the exam will be very similar, basically, those problems. In fact, I'll put 2 literally from those PDF, copy pasted. So a third of the exam will be, I'll just grab 2 problems from this list and put them there. So then you have an incentive to do all of them. If you do all of them, you will not find anything surprising at the exam. Now, because someone had asked me about solutions, yeah.
Oh, yeah.
Yeah, so basically, I mean, for the ones that are the assignments, like if you check, like let's see, if you go to the mirror side, like okay, so if you go to the mirror side for this Canvas side, you click on assignments. So I put say like the solution to that to those problems. Like those are being taken from that PDF. So by the end of like, I will probably create like another, like you'll probably have 3 assignments before the midterm. Like I already had posted like the second one, which is due this week, I think. So there will be another one due, a third one due before the first midterm. So I'll put the solution to those all of those. So that's kind of already 12 problems, and then we will have next Wednesday because like some sort of review session, so I'll do some more other problems on the PDF. So between that, I more or less you would have like half of the problem solutions for it. And that's kind of like a ratio I feel comfortable with, because I don't want to, kind of literally give a solution for every single problem. That kind of ruins a lot of like, of course, you can ask me during office hours or whatever before or after we start class, but at least written solutions, we more or less do have like solution for half of the problems. And the other, I mean, kind of similar, but yeah, like I'll say that. But yeah, it won't be, especially because this is the first midterm. At most, like if there's like a true false, I mean, there might be like a true false question, but it wouldn't be more than one problem. I mean, it won't be that conceptual. That's what I'm trying to say. It will be more like doing some computations, things like that, and then we'll take it from there and see. The second midterm, like probably, yeah, would be a little bit more like emphasis on certain concepts, but for now, it's just like more like, can you do matrix multiplication? Can you find the inverse of a matrix, which I'll tell you about how to do that this week probably. How do you solve a system, which I'll tell you about today. So like more like how can you do things, kind of question. But it won't be that different from, again, from the problems on this video. Okay. It will, so, but yeah, it will be 6 problems, and 2 will be from this space. Okay, so let me stop sharing and go back, and I can finally tell you how to. Okay. I can tell you how to solve systems finally. Yeah, so my idea for today was just to do some examples, and the next time I'll give you some of the theory behind it. just to show you that it's more or less the same thing every single time that you need to do. Okay, so how do you solve a system of equations? So let me start with a very concrete thing. So that we can get a good idea of what's going on. Let's say I give you this system. So the first thing that you need to know how to do is like how to just represent this as a matrix type system of equations. So again, to represent this as a matrix, like what you literally do is like copy the coefficients in front of x, y, and z, and those will become the entries of the matrix. So this is the same as 2, 5, -1, 1, 1, 3 times the vector x, y, z equals 3, 5. Okay, so here this is your matrix A. This is your unknown vector, and this is the vector B. Is that making sense? So everyone, again, needs to be comfortable with that, and that's like the first step. And now the idea is like to solve these systems in a way that kind of becomes standardized. So you may, I mean, you kind of also know how to solve this like in high school, probably, like, you could like say solve for x in this equation, substitute into the first equation, like do some sort of like substitution method, whatever. And that does work, but we just want to come up with a method that it will do the same thing over and over and over again. So like to reduce like the number of like, possibilities in which like how you could try to solve this. So it's kind of like just to systematize like these methods for solving systems of equations. Okay. So what's going to happen is that we're going to do some manipulations on this matrix. Okay. And essentially what we're going to be doing is like altering the coefficients that you see here, like the entries that you see here. So just as a thing of convenience, nothing is going to happen to x, y, and z because, like, say we turn this you'll see what will happen soon, but like say I want to turn this number 2 into a 3. What that means is that instead of having 2x, I would have 3x. So x, y, and z are kind of always there. It's not that x will become x squared or root of x or something like that. Like x, y, and z continue being x, y, and z. That's why this is called like linear equations, because you never raise them to any power or do anything weird. So it is useful to just like forget about them, like when you're writing this down, and you rewrite this system in the following way. So that's like the first thing that you do, like as some sort of like simplification, like to save yourself some space. So you rewrite this. as the following. So you still copy the same coefficients, like, or entries, 2, 5, -1, 1, 1, 3. And instead of like putting X, Y, Z, you forget about those. And you put like a vertical line and then just copy the coefficients of the vector B. So, and this is called the augmented matrix. So like the idea is like in this format, like you put like the matrix A here, and then you put like a vertical line. And then just whatever this vector B is supposed to be. And the point is that you can kind of recover or read immediately the equations from this format because these are just like the numbers in front of X, Y, and Z, right? So this is always like 2x plus 5y minus z. And this is just being said equal to the number 3 that you see there, right? So it is kind of like easy to reproduce the equations from like this way of expressing it. It's like the coefficients in front of X, Y, and Z, and the vertical line just separates those the things that involve the variables to the constant that they're being set equal to. So that's like the role of the vertical line to keep them separate. Is that making sense? So far, so good. Okay, and now the goal is kind of like a game. Just try to make this as close as possible to the identity matrix, and you'll see why we want to do this. So the goal is to make this as resemble, look as close as possible to the identity matrix. Make the system look as close as possible to the identity. So what were these identity matrices? Like, if you remember them, they were like, for example, I2 was like 1, 0, 0, 1, and I3 was like 1, 0, 0, 0, 1, 0, 0, 0, 1, right? I mean, in particular, there were square matrices, right? And this is not like a square matrix. So what I mean by making this as close as possible to the identity matrix is that what's the characteristic of the identity matrix? That there's kind of like one in every row and column, and then a bunch of zeros, right? So essentially, what I'm trying to do is like going to create as many ones. I mean, just one per row or column, and then like the rest as zeros, as much as that can be done. Okay, so try to get one on the say on the columns on each column and zeros elsewhere. And zeros elsewhere. This can, like, not every single time this would be done perfectly well, but we're just trying to approximate this as much as we can. Okay, so it's like a goal. Sometimes we literally would get the identity matrix, other times we'll be close enough, but not quite there. But like you'll see, like, you know, it's kind of like once you see a couple of examples, you immediately recognize when this is over, like the process is done. Okay. So far, so good. So if you look at any identity matrix, right? The first entry and the first row, first column always starts with a 1. So the question is like, can you make a 1 appear explicitly here, right? You're trying to put like a 1 here. So there are a couple of ways you can do this. How could you make that first entry be a one? Any ideas? Yes.
Drop the first row. Second row from the first row.
Well, that's one option. Another option?
Divided by
That's another option. Another option.
matrix.
That's another option. Right, good. So many options, right? So actually I will start with the last answer, which is like the flip. So I mean, like the fact that this is called the first equation and this one is the second, called the second equation is kind of like a convention, right? Like you could have called this a first equation and this the second, right? Like solving a system of equations cannot depend in which order you write the equations, if that makes sense. So there's like a first operation that is literally just that, just swap the order in which the rows appear, right? So the first operation, and that's kind of the easiest one that you could do. So that's why I'm starting with that one. So I'm going to put this operation, which is like the way we would write it is like this. I'm going to put row one. So what this would mean is that I'm just going to swap row one and row two, right? So it's just again changing your mind about which one is the first equation and which one is the second equation. So what like the second becomes the first, so you put 1, 1, 3, 5, and the second becomes the first. Sorry, and the first one becomes the second, so you put 2, 5, -1. Is that okay? Is that making sense? Is it clear that, I mean, if you solve this, like what I'm like solving this system is the same as solving this system, it should give you the same solutions because you didn't do anything to the equations except like, relabeling them, like, calling one the first one and then the second, and you just change your mind of which one goes first. Okay, so it doesn't affect. I mean, the idea is like we're going to do operations on these things that won't affect the solutions, right? Because if we affect the solutions, then it's game over. So it's just like you don't want to destroy the solutions, and just changing your mind about which one goes first and second, like that's fine. Okay. So the first goal has been achieved in the sense that now this starts with a 1, right? So this looks now a little bit closer to how the identity matrices look like, right? Because they also start with a 1. And then once you have a 1, the point is that you use that 1 to create zeros everywhere else in that column. So let me write that down. Once you have a 1, you use it to put zeros everywhere else on that column to which it belongs. You use it put 0 to create zeros in the other entries of that corresponding column. Okay. Because again, if you compare to the identity matrix, like below this one or this one, there are a bunch of zeros. So we're trying to recreate that. We're trying to make that happen here as well. So there's just another row to worry about because there's only 2 rows in this matrix. How do you put a 0 here? How do you make a 0 there?
Second row and you subtract 2 times the first row.
Right, like again, like think about when you were like just to make a baby example of this, like imagine I have given you like if the system had been like x plus y equals 4 and x minus y equals 3, right? One easy way to have solved this system, right, was kind of like, or let me put it like minus x plus y. One easy way to solve the system would have been like say, oh, you just add up the equations, right? When you add up the equations, you get 2y equals 7, and that already gives you the y 7 halves. So like when you are solving equations, you're allowed to add them up, right, or subtract them. What we're going to do now is essentially the same, but instead of like just adding them up or subtracting them, we are allowed to also like multiply them first by a scalar or a number before doing the addition. So let me write that down. So what I'm to put a 0 here, I'll multiply this equation by -2 and just add it up to the second equation. So let me write that down as the following thing. So this is how it looks in practice. You're going to take -2 times the first row, add it to the second row, and replace that in the second row. That's what's going to be the new second row. So like the way in which it's written down typically is something like this. So this just means like this is the thing that's going to be written instead of our like the row 2. So first, like nothing is going to happen to the first row. So you just copy it again as it stands. The first row is being left unmodified because the effects are going to take place on the second row. And then what this means is like multiply each coefficient of the first row by -2. So when you do that, you put like -2, -2, -6, -10, right? And these numbers are being added to the coefficients of the second row. So this, like, what were the coefficients of the second row? 2, 5, and -1, and 3. So is that clear what's going on? So it's just literally multiply everything first row by -2, copy that below, and just add up the original entries of the second row. Well, let me give you a second to copy this. Because what happens when we do this, we get nothing happens to the first row again. So it's 1, 1, 3, 5. But now the second row looks like 0, 3, -7, and then -7, right? So now that's like the new second row. Is that making sense? Questions on this? Now, if you were concerned about whether or not you have the same solutions, right? The idea is that there's actually like a way to go back, right? If you regret what you did, there's like a way to reverse this process, right? So imagine if I had given you this matrix, right? If I gave you this matrix, how would you get back this one? What would you do to go from here to there? So going the opposite way. What would you do?
You add like, is it like half the row?
Right, like for example, if I want to go from here to the one I started with, just take the first row and add 2 times to the second row. Because like you get like 2 plus 0, which is 2, then 2 plus 3, which is 5, and then 2 times 3 is 6, so 6 minus 7 is -1. And then 2 times 5 is 10, 10 minus 7 is 3. And so, and that makes sense because that inverse of -2 is 2, right? So instead of doing -2 row 1, you're to go backwards, you do 2 row 1. So I'm just mentioning this so that you, like, obviously in practice you wouldn't want to do that because like you're trying to simplify the system. But what I'm trying to say is like the operations we're doing are kind of always reversible. that you can always return to where you had started if you regret your decisions, okay? So, I mean, that would be theoretically useful next time, but for now, it's something you can ignore if you want. But I'm just trying to say, like, we're not doing something that destroy, like, you have to imagine, like, in terms of information, we're doing something that gives you still the same amount of information. You're not creating information or you're not destroying information. It's still the same system, just being re-expressed in more convenient ways. Okay? So now this looks like 1, 0. Right, so now it kind of agrees to with the first column of the identity matrix. So our quest we're going on the right track because this is looking more and more like the identity, right? So the next step is that you see, oh, there's a 1 here. So let's try to make a 1 on the corresponding slot, and then use that 1 to kill everything else in that column, and then you'll see what happens. Okay, so so if you're right, if I want the number 1 here, what should I do to put the number 1 here?
Divide the second row by 3.
Yeah, so divided by 3 or like multiply by 1/3, depends on, doesn't matter how you want to say it. So I just want to do 1/3 of row 2. And that's kind of clear enough that, I mean, this is like already tells you what is going to happen. So like you don't have to think anything else, but let's see. So if am I going to do 1/3 of row 1? Again, that means that of row 2, that means that row 1 is left untouched. So it's 1, 1, 3, 5, right? And now row 2 becomes what? It becomes 0, 1, -7/3, and -7/3. Okay, is that making sense? And we're almost there, right? Now, since we have a 1 here, the idea is again to make zeros everywhere else in that column. So the idea now with that 1 is to make zeros. So use this 1 to make zeros. To make zeros everywhere else on that column. I mean, this is a small system because it was only 2 rows, so there's not, I mean, this is why I started with something simple enough for you to get like a sense of what's happening. But so that's like what I'm trying to say is that there's really only one more thing to take care of, right? Which is that we want to see a 0 here. So how do you get a 0 there? What did you do? Right, like you could multiply the second row by -1, right? So do minus row 2. And you add that to the first row. And that is going to be replacing the first row. So let's put it like this. So again, since there's nothing happening to the second row, you put 0, 1, -7/3, -7/3. And now what they're saying is that multiply everything in the second row by -1, so you get -0, -1, 7/3, 7/3, and that becomes, and then you add that to the entries of the first row, so you put +1, +1, and then +3, and then +5. Is that okay? And what does that give us? Let's see. So you see, like, it's a lot of arithmetic. It's not too bad, but it's some non-trivial chance of like just making a mistake because there are so many multiplications and subtractions that you have to be doing all the time. So you just have to be a little bit like careful when you're writing this down. But this gives you 1, this gives you 0, this gives you what? 9 plus 7 is 16, so 16 thirds. This one gives you 15 plus 7, 22, so 22 thirds. And then you get 0, 1, negative 7 thirds, and negative 7 thirds. Is that okay? Okay, and then at some point you kind of realize there's not much left that you can do because, like, say if you were trying to put like a 1 here or here, like you end up affecting what you already did, right? So there's no way to keep simplifying this column, the last one, without affecting the previous one. So kind of like the way in which, again, because we want like a systematic way to do this, we kind of move from the first entry everywhere else, right? So we are always moving like kind of from left to right or up, higher levels to lower levels. So you kind of like are zigzagging through the matrix. So there's no way to affect and to change this column without affecting the previous ones. So you're done. But the idea is like you to realize that throughout this entire process, you were always preserving the solutions to the system. So if you rewrite this back into the format involving x and y and z, this is 1x plus 0y plus 16 thirds z equals 22 thirds. And this one is 0x plus 1y minus 7 thirds z equals negative 7 thirds. Is that okay? And it looks a little bit bad, but just because I'm writing the things that have 0 next to it, right? So if you ignore the stuff with 0, this looks like x plus 16 thirds z equals 22 thirds, and y minus 7 thirds z equals negative 7 thirds. Is that okay? Is that making sense? So imagine that like we had started the problem with that system of equations, right? How do you solve that system? What's the easiest thing you can do now?
That's the 0 solve for x.
Yes, I agree to what you said, 50%. Anyone else? Yes, although here, well, maybe for answer, anyone wants to give it a partial truth between the two answers. Anyone else? Oh, you want to give it a shot?
You can set any of the variables to literally any value and then solve.
Yes, that's more like what I was going for. Right, like the thing is like the way it's presented, right? Like the easiest variable to solve in terms of is z because like it's like the one that's everywhere in the two equations, right? So you could say, for example, here that x is 22 thirds minus 16 thirds z, and y equals minus 7 thirds plus 7 thirds z. And that what that means is that once you give z the value, whatever value you want, like it could be 0, for example, or 1 or whatever, once you give z the value that you want, that fixes x and y to take specific values, right? So the idea is that you think of z as a free variable, right? It is free to be whatever you want, and then x and y are fixed. Okay, so what that means, since you can give infinitely many values to z, this means that this system has infinite solutions. Is that making sense? So, like, let me write that down. So, once you give a value to z, the values of x and y are fixed, right? So how many values can you give to z? Well, infinitely. It could be 0, 1, -1, 3, 5, root of 2, negative root of, like, this is where you start seeing why there are infinitely many solutions, like this like trichotomy of that it jumps from 1 to infinite solutions. So then this is an example of a system with infinite solutions. So this is an example. And help, I mean, the way in which you can write the solutions is like you say, well, what is x, y, z? We know that x has to be this, y has to be this, and z is just z, right? It's whatever it wants to be. So here you write something like e arbitrary. So that's a way to write the solution to this system. Is that making sense? Any questions about this? And remember that the original system, if you want to see it, right? What was the original system, right? Let me write it next to this one. So the original system was 2x plus 5y minus z equals 3, and x plus y plus 3z equals 5. So, like, the thing is, like, if you see it in its original version, it's not okay. You can say, well, let's solve it. It's not so obvious how you solve it because, like, there are like 3 variables involved in each equation. So you could write x in terms of y and z, and also here x in terms of y and z, but then it looks like you need 2 variables, but you really only need 1, right? Because there were simplifications that could be made. So that's the thing with why you try to get it as close as possible with the identity matrix, because since the identity matrix has so many zeros, many of the variables just go away, and then that's just easier to solve for the variables. Is that making sense? Let me show you geometrically how the third side before doing another example for today. Okay. Let me share GeoGebra. Oops. This is another one that I Let's see if this works out. I think this is. Just turning it on and off to see if this makes a difference or not. I'll show you. Oh, good. This is what I want. Perfect. So if you go, if again, you can do it on the computer version of GeoGebra. I mean, like the online version, but I prefer to do it when the one you can download on your computer. So let me go to the 3D view. So like one of the original equations of the system was, I don't know if you see me typing like this, just check what I'm writing in the input. 2x plus 5y minus z equals 3. So you see you have this plane, right? So the first equation represents a plane, is like what you see on that left column. And then the other equation is another plane, x plus y plus 3z equals 5. So you see that other plane, right? So it's clear, I mean, in general, if the planes are not parallel, two planes intersect on a line, is the line that you see there, right? And now what's that line? It is like, you can also write it on GeoGebra. You just have to use like, a line is a special case of a curve. So there's like a version on GeoGebra for entering a curve. So like I'm going to call curve. And now I just put like the entries of the vector that I was writing before. So you can put like 22/3 minus 16/3. And that was z, right? But it's normal to call that t, like this is standard convention, because you can think of this as time. So instead of calling it z, I will call it t. So 7/3 t also minus 7/3. That was the third entry. Sorry, the second entry, and the third entry was z, but now z is being called t. So you call this t, and then t goes from say -5 to 5 to just give you an idea. And now you see the line, right? So it does look, let me rotate this a little bit so I can actually like hide this. Now it looks a little bit better, right? So you see the line of intersection between those two planes. Okay, and now the idea is that if you can keep this line as shown here. Let me hide the planes. So there's a line there. And I now enter the equations that we got at the end, right? So what were the equations we got here at the end? It was like x plus 16/3 z equals 22/3, and y minus 7/3 z equals minus 7/3. So you see, you get two different planes, but they still are meeting at the same line, which kind of makes sense. So the idea is that you started with two planes, right? And the operations that we do on the matrix modifies the planes, but in such a way that their line of intersection remains the same. So in fact, you can, like, again, like, I don't know why GeoGebra is not letting me change the colors when I show it on the computer. But you can show the four planes at once, and you see that they all meet like on the same line, right? So that's the idea. Like you start with like the idea with the matrix operations. It's like you kind of modify the planes to make them easier to work with, but the solution set or whatever, like the intersection, is still fixed. Okay, so that's kind of like what's going on. That's kind of cute, right? So that's one way to think about this system. The other, I mean, because I don't want to be unplugging this computer, especially if this stops working. The other thing I was going to say is that if you go to Wolfram Alpha, I mean, what we're doing is called the row reduced form. I'll give you that terminology next time. or the row reduced matrix. So you enter a Wolfram Alpha row reduced matrix, and then you give like the entries on the row. So you like the original entries were let's see, it was 2, 5, -1, and then 1, 1, 3. And it spits out the one that we found, right? So as a way to check if, you can just randomly enter some numbers, right? As the initial matrix and do the operations to see if you get like the row reduced form. I mean, again, this will be called the row reduced form next class, but it is like a convenient way to check your algebra or arithmetic, because it takes like less than a second to do this, right? And then right, like in applications, and the matrices may have thousands of entries, right? Like data collection, whatever, like or pixels on an image, and then the question is, can you do this efficiently or things like that? But for something like this, it's like for a computer, it would take like you saw it, like nothing in terms of time. So let me stop sharing. And let's go back. Okay, so in the last 20 minutes, let me do another system, another example. And then next time, what I'll do is give you a little bit of the theory. When do you give you like a systematic way for you to know when would you expect to find a 1 solution, 0 solutions, infinite solutions? Yeah. Sorry? The homework? Well, yes, if you ask me during office hours or after class.
When are all the hours again?
They're on the syllabus, but there's some today from right after this class ends until 5 p.m. They're on back call. It is, where is back call? This, but yeah, it's on the, I mean, if you wait until after class, I can also help you here, like before, like, so that you don't have to go all the way back home. Okay, so yeah, we have enough time to do one more example. Now, since you have had like a little bit of experience with this, like we can go a little bit faster with solving it. So yeah, let's do this one. Finish today. So let's solve okay. This one. Okay, yeah, let's solve this one. So again, the first thing is to turn this into a matrix. So like the augmented version, so this becomes 1, 2, 3, 2, -1, 1, 3, 0, -1, and then 9, 8, 3. Does that make sense? And again, the goal is to make this as close as possible to the identity. We're already on the right track because this is already started with a 1, right? So that's good. So the idea is to use this one to produce zeros everywhere else on that column, right? So you want 0 here, you want 0 here. How do I make a 0 here? Minus 2 times row 1 plus row 2, right? So you do minus 2 times row 1 plus row 2, and that's going to be replacing row 2. And the thing is, like, to make a 0 on the third row, that has nothing to do with the second row. They're kind of like independent operations. So you might as well save yourself some space, some time, do it like right away. So let me do also minus 3 times row 1 to row 3, right? Replace that into row 3. Is that making sense? Because like they're kind of separate things. Like one is going to be happening to row 2, the other is going to be happening to row 3. They have nothing to do with one another. So you can do like the 2 operations at the same time. So if you do this, just to go a little bit faster, you get 1, 2, 3, 9. Right? Nothing happened to the first row. And then, okay. Minus 2 plus 2 becomes a 0. Minus 2 becomes, this is -4 now. -4 with -1 is -5. -2 with 3 is -6. -6 with 1 is -5. And then -2 with 9 is -18. -18 with 8 is -10. So that's the end result on the second row. Is that making sense? So there's a lot of operations that happen in your head, right? When you're copying this, like this is where like the risk appears. Like you just like you're doing this mental on your head, and then like when you type it on your paper, like you just make a typo. And then -1, 3, -3 with 3 becomes 0. -3 with 2 is -6. -6 with 0 is -6. -3 with 3 is -9. And -9 with -1 is -10. And then -3 with 9 is -27. And -27 with 3 is -24. So those are the entries for the third row. Is that making sense? Okay, so in the quest of getting the identity, we're getting close to it because like now the first column is identical to the first column of the identity matrix, right? So this is good, this is good, this is good. Our next objective is to make this a 1 and then use this 1 to make zeros and zeros here. Is that kind of making sense? So it's always like create a 1, make zeros, create a 1, make zeros, create a 1, make zeros. Like there's no way to get lost after you have done this a couple of times. It's always going to be the same method. So to create a 1 here, you can divide by -5, right? So you can do and nothing else happens to the other 2 rows. So let me copy them as they are. 1, 2, 3. 9, 0, -6, -10, -24. And then you get 0, 1, 1, 2. Does that make sense? Okay, and yeah, we can use this 1 to make a 0 here, and this 1 to make a 0 here. Again, there are separate operations because they're going to happen on those 2 separate rows, independent rows, so you can do them at once. So I can do minus row 2 plus row 1, and that gets replaced into row 1. And then I can do my 6 row 2 added to row 3 and replace that into row 3. So again, now row 2 is being left untouched, so let me write it down first, the same way. And so now you do -0 plus 1 is 1. -1, oh, sorry, this should have been -2 times row 2, right? Sorry. There's a minus here. It's that, I think. So now it's -2 plus 2 is 0. Good. Then -2 plus 3 is 1. And then -4 plus 9 is 5. Okay. Right, so we needed a -2 here. And then 0, 6, 0 is 0, so 0 plus 0 is 0. 6 minus 6 is 0. 6 with -10 is -4. And 12 with -24 is -12. Is that okay? And we're almost there, right? So now I just want to make a 1 here, and once I got my 1 there, I'll make the third column, the remaining entries on the third column zeros. So how do I make a 1 there? Like I could do like third row divided by -4. Okay. And finally, yeah, use this one to make 0 and 0. How do you make them? Well, let's do minus row 3 added to row 1. And replace that into row 1. And let's do minus row 3 added to row 2 and replace that into row 2. And the third row was left untouched. And now this becomes 1, 0, 0, and then 5 minus 3, 2. And the other one is 0, 1, 0, and 2 minus 3 is -1. And now this one is even better than last time because this is literally the identity matrix, right? If it was like a perfect like this is like identical to it. So the system, if we rewrite it, it's just saying that x equals 2, y equals -1, and z equals 3. And that one, yes.
Divide by -4 when you already have a value for set.
Oh, right, like from here, okay, right. From here, you can kind of set z immediately the equals 3, but at the same time, you know, if you rewrite, like once you know z equals 3, you kind of have to do some operations like in the other two to. So that's always better. I mean, this is just takes a little bit maybe more steps, but it just leaves it so clearly, like gives you right away the answer that is like the payoff for that. Is that making sense? And so in this case, there's a unique solution because we had no freedom of what the variables could be. So in fact, this is going to, I mean, again, like next time I'll give you more like some rules of the game, but like the idea is like if you had like a system with the same number of rows and as unknowns, right, where like it's like a square matrix and you get to the identity matrix, you do get like a unique solution, for example. And also this secretly will give us an algorithm for finding the inverse of a matrix. Yes.
Is there a way to check our work, make sure we didn't make a mistake?
Well, yes. Take these numbers, plug them in here, and see if it works. So it's 2, minus 2 gives you 0, and 3 times 3 gives you 9, so it works. So the first equation is solved, and so on. That's the only way you could check. You just go back to the original system and plug in what you found here.
It's always possible to put one to one with that.
It's actually only possible, but for example, in this case, I'll give you like the rules next time. But for the case of like the square matrix, it's only possible when the matrix is invertible, in fact. So this matrix, the one that you see here, this 3 by 3 matrix has an inverse, which I'll tell you later how to find it. But if you manage to get to the identity, that meant that it was invertible. If you had found like it could have occurred that you get 0, 0, 0, that also can happen. So it would have had like infinite solutions in this case. I mean 0, 0, 0, 0. I mean there are other possibilities that can occur. I was teaching you just how to solve the systems, right? So next time what we'll do is like some sort of interpretation to anticipate when would you see like 0 solutions, 1 solution, or infinite solutions, right? But what I'm trying to say is that no matter how many equations, unknowns you have, what the numbers are, you always do this, and like there's no way to get lost after you have tried it a couple of times. Like it is like a very algorithmic process. Yeah. This is actually at the beginning of like chapter 1, somewhere in chapter 1. I'll send like when I send the announcement, I'll refer to the section of the book. But yeah, it's like at the very beginning. As I said, I changed a little bit the order, so this is kind of like where the book starts. It's just like I find this very annoying to do at the beginning, so like that's why I changed things around. But yeah, it's like a 1-3 or 1-4 or something. Yeah. Okay, so yeah, I'll see you on Wednesday. And again, if someone wants to ask me anything, I'll say a little bit here until this gets uploaded. So.